Okay, now we're gonna find the limit from two different sides. So for example, this one, this says limit as x goes to 2 from the negative side of f of x, and limit as x goes to 2 from the positive side of f of x, where f of x is defined as a piecewise function, where if x is less than or equal to 2, it is this parabola, and if it's greater than 2, it's this linear function. So let's look at this graphically to see how this is going to look like. So I'm not going to take a lot of time trying to graph this, so I use decimals to help me figure out how it looks like. And this graph looks like this. So if it's kind of good review of piecewise functions. So on the left of 2, so basically if you break this graph into two, stopping at 2, on the left of it, it looks like negative, this parabola that is pointing down. On the right, it looks like 2x minus 3. And again, with the help of decimals, I just want to show you how it looks like. You really will not use the graph pretty much anytime in constructing a graph to figure out the answer. Okay, so it looks like this. Obviously, it's a piecewise function, so you cannot have a point overlapping, which means you see how here I have a open circle on one and closed circle on one. You cannot have two closed circles because then it would not be a function. So this is how the graph looks like. And then if you are looking at what the limit is going to the function from the left hand side of 2, you can see that if I try to, so on the left hand side of 2, that's this graph, and I'm following it to where it stops at 2 from the left hand side, you can see that this limit is going to be 3. And then on the right hand side of 2, that means the plus side, you're following this graph, and then it goes down to 1. Okay? Now, we don't want to draw a graph every single time when we're doing limits. So what we want to do is look at it algebraically. So limit as x goes to 2 from the left-hand side of f. So left-hand side of f, that just means every number that is, left-hand side of 2 means every number that is smaller than 2, that is this function, using that function. So first you look at the function and say, is it going to be undefined at 2? If it is, we had to use the skills that we learned before. It is not, so we're just going to put it in. So f of x is this function when it's coming from the left. So plugging in 2, so this is negative 4 plus 8 minus 1, which is 3. Please be careful here. I know this is a very small algebra thing, but a lot of people make this kind of mistake. We're just putting 2 into the function of x squared, and then the negative is attached at the end. So please don't put negative and square the negative. All right, so now limit as x goes to 2 from the positive side of f of x. So from the positive side means all the numbers that's bigger than 2, which means we're going to use this function. So this is going to be limit as x goes to 2 from the positive side of 2x minus 3. 2x minus 3 is also not undefined at 2, so we can just plug it in. So 2 times 2 minus 3, that is 4 minus 3, which is 1. Which is true according to our graphs. That is where the limits are. All right, now that you know what to do, go ahead and figure out the limit for limit as x goes to 1 from the negative side and x goes to 1 from the positive side of f. So stop the video, do the work, and come back and check. All right, here are the answers. Please double check. All right, so next one, find limit as x goes to 3 of f of x and prove that f is discontinuous at x equals 3 for this piecewise function. So how do we prove that something is discontinuous? Well, let's think about what discontinuity looks like. Or let's think about what continuous looks like. So continuous means that the graph has no stop, right? So you can draw the graph with one pencil stroke and it will not, you don't need to pick up your pencil. Now, what is discontinuous then? What are the different kind of discontinuity? Well, we have the removable discontinuity, right? So removable is either like this, or I'm sorry, removable is something like this, or something like this, right? So there's a hole. Or we could have a jump discontinuity, or we could have infinite discontinuity. So if we want to prove that something is discontinuous, we have to prove that at that point, something happens. Now, what do we see when something is discontinuous happening? Here are the three, the places where it's discontinuous, right? So what's going on at that point? Well, what is going on is that for this one, there is a hole. So if we want to prove that it's discontinuous, we had to prove that there is a hole. And same thing here, there's a hole. This one, the third one, we basically can say that this point and this point are not the same. So then there's a break, right? And then this one is a little different. We would have to say that it's not even going to a number. It's going somewhere else. So without getting into a ton of calculus, which we'll get to next year, to prove that something is discontinuous, there are a few things. So to say that something is continuous, so if you want to prove that something is discontinuous, you just have to say that why it's not continuous. So to be continuous, there are a few things. First, the limit as x goes to a number of a function has to equal the actual number at that function. Okay, what does that mean? So remember, when we talked about limit, we said it basically is what the function, where the function is trying to go to from both sides. So the key word is trying, which means we don't really care if it's ever gonna get there. So a lot of times, from the previous lesson, you can see that even if there is a hole, we would still say that there is a limit. So limit just means where the function is trying to go to. So limit does not mean that it's continuous, right? Because a hole is not continuous. So first, if we want to prove that it's continuous, then the limit, which means both sides going to the same number, has to equal an actual value at that number. Okay, so what does that mean? So that means, let's say this point here is A. So the left-hand side is going here, the right-hand side is going here, so there is a limit, right? There's a limit because they're going to the same point. And it's continuous because that number it's going to is also the same number that the graph actually has a actual point that exists there, right? The same exact number. So then we would call this continuous. Okay? Now, that's great. That basically proves continuity. But the second thing is you have to show that the limit is that number. And how do you prove that the limit exists at that number? So remember from the lesson yesterday, to prove that the limit exists at that number, we would say the left-hand side goes to some number, which is equal to the same number if you come from the right-hand side. If that is true, then the limit at that number is the same. I'm sorry, I keep saying the number. I should be more clear on x. So the limit as x is going to a, okay, a is an x value from the left-hand side, is equal to the limit as x goes to a from the right-hand side. So that means they're both going to the same number. And if that is true, then the limit must exist at that number, and we call that a. We call that the same limit. So first you prove this one, then you can say, oh yeah, there is a number. There is actually a number that exists at f. Then is there an actual point at that same limit? If there is, then you can say that it is continuous. Okay, so this is a long explanation about continuity, but it's a very, very important concept. So if we want to prove that this is discontinuous, it just needs to break one of them. Either this one, or this one. If you can show that either one is not true, then you can say that it is discontinuous. All right, so if we want to prove that the either one, let's just start with I guess the easy one, that we had to find the limit. And to find the limit at that number, and that is 3, because it's asking us what's going on at 3, is it continuous or not? So we have to figure out the limit at 3. And to figure out the limit at 3, we have to figure out where it's going from the left of 3 and where it's going from the right of 3. All right, so limit as x goes to 3 from the left-hand side of f of x. Okay, left-hand side of f. Left-hand side of 3 means number smaller than 3. So if you look at this piecewise function, where is which piecewise function will represent the function for x that is less than 3? That would be this one, right? Because this says everything that's not 3, use this one. If it is 3, use this one. So everything that's not 3, which includes numbers smaller than 3, we're going to use this one. So we're going to put 3 in there. 3 squared minus 9 over 3 minus 3. This is going to be undefined. Does undefined mean that it doesn't have a limit? No. So remember back in the first section, how do we find a limit if it ends up being like this? That means we got to use some other method. We would, according to the first section, we would factor and simplify. And then we put 3 in there. 6. So limit as x is going to 3 from the negative side is going to, the limit is going to 6. Now let's look at the same limit from the right-hand side of 3. Well, from the right-hand side of 3, we would still use the function that says use this when x is not 3. So then we would still get 6. So if the left-hand side and right-hand side are going to the same place, then that tells us the limit as x is going to 3 is also 6. According to the continuity theorem, the left-hand side and right-hand side going to the same number, that shows that there is a limit. However, if you want to prove that it's continuous, that limit has to go to an existing number at that function. All right, so what is the number at 3? So what is f of 3? Well, it says when x is 3, f is 2. So that means f of 3 equals 2. You can see that the limit and the actual numbers are not the same, which means that it's discontinuous. Okay, that is very, very theoretical. So let me show you how this graph actually looks like at 3. So x squared minus 9 over x minus 3 is really just this function. So, oops. Okay, so this is the piecewise function. Everything besides 3, use this one. And then at 3, use 2. So this is what it looks like. So you can see that when the limit as x is going to 3 from the left-hand side, is y is going to 6. And when it's coming from the right-hand side of 3, it's also y is also going to 6. But the actual number at 3 is 2. So we have a hole, removable discontinuity. So we just showed that this is discontinuous. All right, so maybe let me show you another one. This continuity is kind of the hard thing to learn for calculus. Okay, does the limit exist for f of x at 1? And then you have this piecewise function. If so, give its value. If it doesn't exist, give the limit from both sides of x value. Okay, so does the limit exist? Okay, it's not asking for continuity, so then you just have to prove that x is going to 1 from the left-hand side and 1 going to 1 from the right-hand side. And if you want to show that it exists, the limit as x goes to 1 exists, then both of these numbers have to be exactly the same. If they're not exactly the same, then just tell them what number they are. So go ahead and do this one. This is a very simple problem. Figure out the limit from both sides and then make a decision. Is there a limit as x goes to 1? Okay, a very simple calculation. You can see that as x goes to 1 from the negative side, the y is going to 1, and then as it is going to 1 from the positive side, y is going to 2. Therefore, the limit as x goes to 1 does not exist. Now we have some different kind of limits that we need to cover. So there are limits that involve infinity in different ways. So limit as x goes to infinity, meaning when x is going to the right-hand side, really, really, really far, or as x goes to negative infinity, so going to the left, really, really far, y is going to some number, then we say that there is a limit. So the limit of f of x approaches L as x approaches infinity from the I'm sorry, I probably should change my notes in the future. So we don't need this part. So the limit, so this means the limit as x goes to infinity, y or f of x is approaching L. And then the second one is basically saying the limit as x goes to negative infinity. So we don't really care about what side. It is just going to that number. Y or f of x is approaching L. So let's look at an example. Let's say that we have a function that looks, let's do a very easy one. Let's say f of x is equal to 1 over x. And this is the function that we memorized for so long. Looks like this. So the question is, limit as x goes to infinity, f of x is going to where? So when x is going to infinity, you're going to look at here. So x is going to infinity. So make sure you keep that in mind. It's x going to infinity, not the y direction x is going to infinity. Where is y going to? Y is clearly going to, 0, right? And then same thing here, as x goes to negative infinity, where is y going to? When it's going to negative infinity, we're traveling with the graph to the left, and then you can see that y is going to 0. Okay? All right. Now we can look at this one as well, sine x over x. So as limit as x is going to infinity, where is y going to? So let's travel with the graph to the right. So you can see that the graph kind of goes up and down, but it goes up and down much smaller as it goes farther and farther to the right. So we can pretty much expect that it's going to eventually become 0. Not exactly at 0, it's just saying that it's oscillating a lot smaller as it goes to the right. So we would say that's almost like 0. And then same thing to the left when x is going to negative infinity of f of x. And you can see that as we travel with the graph, it's also oscillating shorter, smaller as it goes. So we're going to say that it also goes to 0. So that's one kind of infinite that involves infinity, where x is going to infinity or x is going to negative infinity. Now the other kind of infinity limit is when x is going to some number, but y is going to infinity. So you see the difference here? The previous problem is when x is going to infinity. This one I'm going to talk about now is y going to infinity. Okay, infinity or negative infinity. So this one that we're looking at here, it says x is going to c from the negative side and y is going to infinity. So this is c from the negative side. And then this one is x going to c from the positive side, y is going to infinity. Okay, how does that look like? So if we look at this example here, 1 over x squared, so let's ask the same kind of question. Limit as x goes to, so this time I'm going to say 0 from the negative side. Where is y going to? So if we're talking about x going to 0 from the left-hand side, negative side, where is y going to? If you travel with a graph, you can see that it keeps going up. So then we're going to call this infinity. And then same thing here, as x goes to 0 from the positive side, where is y going to? So coming from the right-hand side, y goes straight up again. So this is going to be this, infinity. Let's try to bring in what we just learned from the previous problem. So when x is going to infinity and x is going to negative infinity, where is y going to on both of them? Okay, so x goes to infinity. X goes to infinity, we're traveling this way. So this is y is going to 0. And then same thing here, when x is going to negative infinity, y is going to 0. Now, limit as x goes to something and you say y goes to infinity does not mean that there's a limit. So infinity is a huge number, right? It's actually just a placeholder of saying huge number, increasing without bound. So it's not actually saying that there is a number called infinity. Infinity is just infinitely large. So we don't consider infinity a limit. It's just a placeholder of saying that it's really large. So then we will actually say in another way, we can actually, instead of saying infinity, we can also say that the limit does not exist. So this is another, that's, or we can say D and E for short. This is another very important point. So infinity or negative infinity does not mean there is a limit. So if someone says, does this limit exist? You would actually say that the limit does not exist. Even though it's going to infinity, you cannot say, yes, it does exist and that number is infinity. That's not true, because infinity is not a number. It has to be an actual number for it to be a limit. So infinity is not a number. You would say the limit does not exist. If you want to ask me the direction, it goes to positive infinity. So, that's kind of the answer you would give. If you kind of look at this a little more closely, you realize that when x is going to, so these two sets of things, that's kind of different, that involves infinity, right? The first one, when x is going to infinity or negative infinity, y is going to a number, that basically was our horizontal asymptote. We study this since Algebra 2. We're just now learning how to define it using calculus terms. The second one, when x is going to a number and y is going to infinity, we're basically talking about the vertical asymptote. So stuff that you have been learning since Algebra 2, but now you have a calculus attachment to it. All right, so let's really quickly figure these out. So these, you're going to use graphs. So you're going to graph on decimals or graph on your graphing calculator, and you're going to figure out the limit for each one. So go ahead and do that. Pause the video, come back and check your answer. All right, please check your answers. So I put two options for infinity or negative infinity. For both of those, you could also use does not exist as an alternate answer. It's a acceptable answer. For number 3, if you didn't get this, then you just need to zoom out on your graph. This is a logistic graph. So if you remember the logistic functions, there is a capped limit to growth. So this is C, if you remember, that's chapter on exponential functions and logistic functions. So 50 is the cap to growth or limit to growth. So if you zoom out on the graph, you can see that the graph goes like this. So here are those numbers. And that's it for limit. So if you have any questions about limit, especially with the continuity part, please let me know.